All right, shall we? So we ended last time talking about these three like special subspaces that any basis will have, or that any matrix will have. Um, so the null space, the column space, and the row space. We got a little hung up on the row space yesterday, but I think that was mostly calculator stuff. And I don't think any of your calculators did anything wrong. But I was unable to find any reason that a matrix why a calculator would say a matrix could not be reduced. So I don't know, maybe if that's something you haven't resolved, maybe we can look at it individually, but I couldn't reproduce that. So we talked about how to find the null space, the column space. We got a little hung up on the row space, but let's get back into it. So again, I'm using the same matrix that I used for the first couple of examples. So one thing we've already done, which might be of use to us, is the fact that we've already reduced this. So we've reduced this matrix A into this reduced row echelon of 1, 0, 0, negative 1, 5. Other way around. Zero, 1, 4. Did I flip some signs in there? Zero, 1, negative 4, 3, 2. Okay. So when we reduce row echelon, or do Gauss-Jordan elimination on this is the matrix we get. So we're trying to find a basis for the row space. Maybe we should remind ourselves what the row space is. What is the row space by definition of a matrix? The span of the rows, right? And if we're going to talk about the span of something, we can basically the basis is going to be essentially the smallest set of vectors that spans that space. So we want something linearly independent. If we look at A, are these rows linearly independent? I hear a no. Why is the answer no? How do we know we can do that?
Because there's 5 rows and only 3 columns.
Other way, you said 5 rows, 3 columns. The other way around is true. So 3 rows, 5 columns. Because of that we have to have some kind of redundancy. We have to have some kind of linear independence. And the fact that we were able to reduce this into the thing we reduced it to, that should basically, this is going to give us the row space. So we got the column space from this yesterday, right? What was the column space? Or more importantly, how do we find the column space? Should we go back and look at it? Right. So wherever the pivots ended up in the reduced form, we take those vectors out of the original matrix. That's the column space. We're going to do something a little bit similar in this case for the row space. Now that we've reduced this, basically what I've learned is that this third row has no bearing on what the basis of this row space is. So because of that, I can say the row space of A is equal to the only 2 linearly independent vectors that came out of this. So what are those going to be? 1, 0, 0, 1, negative 5, and 0, 1, negative 4, 3, 2. So what's the dimension of this subspace, or the dimension of this basis? When we talk about dimension, it's only one number, not a pair of them. So maybe we should remind ourselves, when we talk about the dimension of a basis, what's the question we're really asking?
number of pivots?
Yes. It is. It does boil down to the number of pivots, and that's because it's the number of vectors that are in this basis. So I have vector 1, vector 2. So more directly, the dimension is how many vectors are in the basis. So I don't think I asked this question for the column space and the null space, but what's the dimension of the column space? 2. Those vectors are not the same order and not even the same number of entries as these vectors, but the dimension is just about the number of the vectors, not what those vectors look like. And what's the dimension of our null space? 3. Okay, so just to kind of solidify what that word dimension means in this context. So in this case, we get in answering all these questions, we've kind of gotten, so far, we've gotten the answers to all of them by reducing this matrix just one time, right? So we've got the null space, the column space, the row space. One more thing I want to show you that we have to treat a little differently. So remember the whole kind of, the way we started class yesterday was to talk about, the way Edfinity wants you to talk about the basis for a column space, even before we started using the phrase column space. You also might be asked for this. Give me a basis for the row space that actually uses these rows. So in this example, we gave a basis for the row space, but it doesn't contain anything that exists in the original matrix. That's something we can do. And this is where we jumped the gun a little bit, and that's my fault. This is where we're going to need to take the transpose of this matrix. So 2, nope, -3, 12, -7, -16. And this is the thing we had some hiccups with. So I will bust out MATLAB if I have to, but I think it's valuable for you all if this is something you know how to do on your own calculator. So what's the order of this matrix?
3 by 5.
A is 3 by 5. So when I transpose it, it becomes what order? 5 by 3. Yeah, we switch the dimensions. So here's what I think we can say for sure when you reduce this. The bottom 2 rows are all 0, right? Because the best you could ever do at reducing this is to get the identity in the top 3 rows, right? You might have more 0 rows, but I think I can say for sure the bottom 2 rows are zeros. Is that a safe guarantee?
Yeah.
All right, so when someone has the reduced version of this, let me know. I did it in MATLAB yesterday. If memory serves, the 3rd row is also zeros. It'll work that time?
I have to delete the bottom row.
You had to delete the bottom 2 rows of the transpose?
Yeah. So good.
What'd you get?
0, 0, 5/17.
Is anybody's calculator giving that to them as is?
Now it's down here.
That's so
I
strange.
might have to do this one.
What's that? What do you mean do it on our own? Like actually do it by hand? I mean, it sounds like if you take off the bottom two rows. So basically, if you rewrite this as a 3x3 matrix, it reduces just fine. Let's make sure.
It feels like kind of strange cutting off like
Here's why I'm telling you it's fine. Let's go back to the question I asked a bit ago. Are we okay with the fact that I'm essentially guaranteeing the bottom two rows are going to be zeros? If that, what's that?
If you put that two columns with zeros, it won't do it. That won't.
I don't care for that. Okay, so reduce the transpose. Great. Right. No, MATLAB doesn't agree.
It's because you have the 5, like the second row, right there should be 9.
Yeah, it would help if I was reducing the right matrix. This one here? Yep. Okay. So we got a couple workarounds if you're trying to reduce a matrix that has more rows than columns. Not sure why that's something that TI can't handle, but we do have a workaround for it. So U7, you made it into a 5x5 and it still gave you the right. Okay. So make it square. It's probably more responsible not to delete things, but to tack on 0 columns. All right. So now that we have corroboration on this reduced transpose, we want a basis for the row space, right? But we've transposed, so now we want a basis for what? Basically, we want the column space of A transpose. Or at least a basis for it. So what's a good basis? Think about the way we've found column spaces in the past. The one we found yesterday.
cool. Okay.
Right, it's going to be the exact same thing. I want to look at the pivots. So what columns do I have pivots in? 1 and 2. So my base is going to be dimension 2, but what are those two vectors going to look like? If the pivots are in the first 2 columns in the reduced matrix, first 2 columns of the transpose. So 2, -3, 12, -7, -16, -5, -1, 4, -8, 23. The last thing to worry about, though, is that we were asked for a row space and we gave columns. So let's do this. What's the row space of A? So the transpose has essentially served its purpose. We're going to go back and re-express these as rows. So 2, -3, 12, -7, -16, and then -5, -1, 4, -8, 23. How are we doing? So the big difference between this example and the last one is what we're restricted to use for the row space. So in this first one here, I want a basis for the row space. Give me any two vectors that make sense. That's what we did. In this one, I'm a little more restricted. I want to use two vectors that make sense, but I want those two vectors to have belonged to the matrix that I began with. Any questions on the difference between the way we go after this? Do there have to be two vectors in each one of those bases? Yes, yeah, that has to be the case. So one thing we brought up last week is that even though there are like many bases for a subspace, they all have the same dimension. So if we found one basis that has dimension 2, any other basis we find has to be dimension 2. So that's what everything that we've done is agreed with that so far. How are we feeling? All right, so let's recap here. How do we find the null space? Or should we go back and look at it? We did some Gauss-Jordan elimination, right? So we did some Gauss-Jordan or reduced row echelon form of the matrix. And then once we finished that, what did that tell us? Or what did that allow us to do? Yeah, so then you can basically parameterize solutions. Because essentially the equation you're solving for the null space is you have your matrix A, you multiply that by your, unknown vector, and what you want is the zero vector. And basically the parameters will tell you everything that fits that. Every vector X that can make that happen. It always includes the zero vector, probably will include more things as well. How about the column space? How do we get that? Also, same. So basically this one process can buy you a lot of these, right? But what did we do differently? So after we had the reduced row echelon form, what did we do differently? I don't think we parameterized any of the rows after that. You're so close. I have such a small protest of what you said. That's the protest I had. I think you said rows. So choose columns corresponding to pivots. And I'll be really clear, columns from what? Yeah, not from the reduced matrix, but from the given one, from A. What about the row space? Can't I just copy and paste all this stuff? Except for one small thing. This becomes rows. So really, Gauss-Jordan elimination or reduced row echelon form buys you all these. You have to do a little bit, you have to do some slightly different things with that reduced matrix, but that's the way to get all these spaces. How are we feeling? All right, one more thing to talk about. These two ideas of rank and nullity. So every matrix has these two things. The rank is really, you can define it in a lot of ways that are equivalent. The one I'll tell you first is that it's the dimension of the row space or column space. Those two things are always guaranteed to be the same. If your row space has a basis of 5 vectors, then so does your column space. So that's what a rank is. The nullity is the dimension of the null space. So how many vectors make up the basis for your null space? And there's a theorem that joins those things called the rank nullity theorem that says this: if you have an m by n matrix and you add the rank and the nullity, that always equals n. So kind of a way you can check yourself, or make sure you have the right number of objects to make up all the bases of all these subspaces. But those two things have to always equal n. So we've only really looked at one matrix today. What's the order of that matrix been? What's the order of A? It's 3 equal to 3 by 5, right? What was its nullity? I believe it was 3, right? The null space had 3 vectors in it. And what's the rank? I think the row space. So we found 2 different row spaces, or 2 different bases for the row space. And the column space, all those things had 2 vectors in it. So does that fit for us? Absolutely. Let's say we have like a generic, like, let's give you an example here. Let's say we have a 4 by 7 matrix. What's the greatest the rank could possibly be? Why 6?
Well, because there's always the nullity of 1, because it's 0, 0, 0.
Okay, so the nullity will always be 1. Are we sure about that? I would say this nullity can be 0 in a very special circumstance. Because so let me put it this way: what's the only vector that has to live in the null space? 0, 0, 0. You don't need any vectors to make that one. Basically, that has a basis of 0. It's a weird way to think about it. But let's think about this. I'm saying 4 by 7, right? So 4 rows, 1, 2, 3, 4. 7 columns, 1, 2, 3, 4, 5, 6, 7. And if the rank is the number of columns in the basis of the column space, think about this: how did we find the column space? It's the pivot values, right? But to find the pivots, I have to. How many pivots could this thing have? It could have 4, right? Could have less, but it could have 4, right? So the rank, the highest possible rank, is always going to be the smaller of these two numbers. How are we doing? All right. I think I just asked you this, didn't I? So what are the rank and nullity of A? I think respectively they're 2 and 3. There were 2 vectors in the row spaces and the column space in those bases, and the null space had 3 vectors in it in the bases. I keep saying the null space had 3 vectors in it. That's wrong. The basis for the null space has 3 vectors in it. The null space has an infinite number of vectors in it. How are we doing? All right. Should we look at a new one? Let's just go from scratch to show that we get a lot of these things. Like there's like one process that kind of branches out into several different things, but there's a lot of commonality here. How would I find the row, column, and null space of this? I don't care in whatever order you want to do it. Reduce. I believe strongly you could do it by hand. I'm having more doubts about whether your calculator will actually do it. So let's make sure that happens.
That's function.
What's that? It sounds like it's okay if the number of rows is less than the number of columns. One negative 2 0 0.
Yeah.
0 0 1 negative 1. Cool. We have corroboration. All right. Sounds good. So here's the reduced matrix. So I essentially asked you 5 questions here. Can we answer any of them yet? Cool. What's the column space? What's the basis for the column space?
1 0 0.
We can't. Yeah. So yes, we rely on the pivot. So the pivots lie in columns 1 and 3, but the column space, those pivots just basically tell us the addresses of the vectors we want. So this first pivot suggests to me that I should take what vector for my basis? Column 1 from A. So -1, -2, -3. And then the other pivot tells me I should take what? 1, 3, -3. So that's the column space, or that's the basis for the column space. Sorry, not the basis, a basis. What else? So yep. Right. The nullity is what? Because why? Here we go. So nullity of A equals 2. So what's the order of this matrix? 3 by 4. So the order of A is 3 by 4, which means the rank and the nullity have to add up to equal what? It's always the number of columns. Which means now if I ask you to define the null space, it should have exactly 2 vectors in it. Do we know what those 2 vectors are? Or do we have to do, actually, we should probably do a little more, take a little more care. With the column space, you can just kind of pluck out those vectors. The null space, I think we have to do a little more defining. So from here, how do we find the null space? Parameterize this. So bottom row gives us nothing. What's the middle row give us? X3 and X4 are equal. What's the top row give us? X1 equals 2X2. So I think that is as simple as we can say what the null space is. But then how do I write that as a basis of vectors? Right. Well, I mean, we've done that. Let's say this. Now let's think about a generic X1, X2, X3, X4 vector. How many parameters do we need? 2. Does that fit with what we said the nullity is? Should, yeah. So I'm going to say that X2 and X4 are parameters, right? So I'm going to just say that I mean, you can rename them to whatever you want, but I'm just going to use X2 and X4 as our parameters. So if x1 equals 2x2, what should the top row of both these vectors look like? Two here, 0 here. What about the next row down? Why is it 1, 0? Basically, x2 equals 1x2 plus no x4s, right? What about x3? It equals no x2s and 1x4. And x4, no x2s, 1x4. So our null space of A is going to be what vectors? Right, whatever we multiplied by these parameters, 2, 1, 0, 0, 0, 0, 1, 1. Okay, so we got the null space, we got the column space, we got the rank, we got the nullity. Can I write a row space? I think I can do it without doing any more work than we've already done. What's a good row space here? Where'd you get that? Or how come why is that something we want to use?
Corresponding to the pivots.
Right. So now instead of looking at what columns the pivot's in, it's what rows the pivots are in. Or another way to think of it, what rows survive? What rows are not all zeros? Those rows are going to contribute to the row space. How we doing? Any questions before we say goodbye to this chapter forever? Or at least till Monday. Okay. So going to chapter 5. If it'll let me. All right. So we're going to talk about these brand new things called eigenvalues and eigenvectors. So let's build up like why they exist, what they're special for. So let's think about this for a minute. We have a 2x2 matrix A, a 2x1 column vector V, and some real number K. How are V and KV related to each other? Think about it in terms of magnitude and direction. Oh, can I not write on this? Why not? Y'all can answer while I'm trying to figure this out. So how is that? I have a vector V, and then I've also another version where I've multiplied it by K. How are those two things related to each other, or are they completely different? Well, a vector has both of those things on its own. So like vector V, even if you don't multiply it by K, has a magnitude. But what happens if you multiply it by K? It scales it, right? So it could make it longer, it could make it shorter. It might alter the magnitude. What if K is equal to 1? It's not going to do anything, right? So the magnitude is in doubt. Those two things might have different magnitudes, right? What about the direction? If I take a vector V and you're essentially telling me that multiplying it by K scales it, what do the directions look like? They should be identical, right? The only way they might be different, if you even believe it's different, is if, let me draw a picture here. Let's say this is V, and let's say K is bigger than 1 and positive. That's KV. Directions are the same, right? What if K is a negative number? It would go directly opposite. So that, when I say the direction is, the same, that's the only way they might be different, is that it'll be on the same heading, it might be exactly opposite. But if you multiply a vector by a constant, you're not going to do anything to the direction. You have some influence on the magnitude, but that's it. You cannot alter the direction. What about if I take a vector V, so V1, V2, and I multiply it by some matrix A on the left? Will the magnitude stay the same necessarily?
Yeah.
Maybe let's get some hard examples here. Someone give me a vector, whatever values you want. 1, 1 sounds good. What if I multiply? What if this matrix is like this, 2, 2, 2, 2? Will this vector have the same magnitude? Are you sure?
No.
What's the magnitude of this one? Do you remember how to find the magnitude of vectors? You can do Pythagorean theorem on them. This side's 1, this side's 1. Radical 2. But if I multiply this by this 2 by 2 matrix, I think I get 4, 4. What have I done to the magnitude? I quadrupled it. So I can clearly alter the magnitude. Is the direction the same? Going up 1 and right 1 and doing that 4 times in a row, like that's going to put you on the same heading. So what if I change this matrix by a little bit? What if I put that number as a 3? Then what's the result going to be? 4, 5. Is this the same direction? No. So when I multiply by a matrix, I can really alter both things, right? So multiplying by a constant scalar will always preserve the direction, but it may not preserve the magnitude. Multiplying by a matrix could have any effect on both. Go ahead.
Yeah, when we're talking about magnitude, we're not talking about optic matrices, right? We're just talking about the.
No, we're talking about how big the vector is. So not only its components, but purely how long it is. So that's like the size of the components in this vector 1, 1 they're both 1.
Yeah.
But if I take its magnitude, which we usually write double vertical lines like this, that's equal to square root of 2.
Nice.
So questions on the difference between those two things? All right. So here's what an eigenvalue essentially is. An eigenvalue is these special real numbers that are guaranteed to preserve the direction in this multiplication. So lambda, this Greek letter lambda, that's what's called an eigenvalue. It's called the eigenvalue because it has this special property that if I have some matrix A and I multiply it by some vector V, it has the same effect as me multiplying some other constant by some constant by that same vector. So the eigenvalue is whatever that real number lambda is. The eigenvector is whatever that special vector is. So they always come together in pairs. Every eigenvalue has a corresponding eigenvector. If you're curious, I think the German word eigen means like characteristic or proper or something like that, basically to highlight the fact that we're not truly altering the direction of this vector. So that's what these things are. Are we okay with that before we talk about how to find them? Okay. So let's let me derive how we go about finding these things. So here's what I want. I want some matrix A, when I multiply it with some special vector V, it's equivalent to me scaling that vector V by this constant lambda. So first way I'll rewrite this is this: AV minus lambda V equals the zero vector. I would like to factor out a V from this left-hand side, but I have to be careful about it because if I factor that out, I can't even factor that direction, never mind. Is there anything wrong with me writing that? What kind of thing is A? It's a matrix. What kind of thing is lambda? It's a scalar. So it's incorrect for me to subtract them like this. But if there is a matrix that kind of has the effect of subtracting a scalar, I can replace it with that. That's exactly what the identity matrix is. So for now, this is now hopefully something that's legal. This is forbidden, but this new thing hopefully gets around that. Now I'm truly subtracting a matrix from a different matrix. So the way this equation is written, what kind of vectors? Give me one vector that V could be to make this thing true. The zero vector, that will always work. If I take the zero vector and multiply it by anything, by any matrix, I will get zero. But I'm not really interested in those. I'm interested in the things that, I'm interested in the vectors that are not the zero vector that still make this product zero. The inverse of this one here. Let's think about that. And I'm gonna first I'll bring this up. So I want to look for the vectors that are not equal to zero that do this. If this A minus lambda I, if it had an inverse, what does that mean about? Yeah, if a matrix can be inverted, what does that mean? The determinant is not zero. And if the determinant is not zero, that means that it can be reduced into what? What's the reduced row echelon form of this? Let's say that it's 2 by 2. Yeah, so if the determinant is equal to anything other than zero, then it reduces into the identity, right? Which means that the only vector that I can multiply by A minus lambda I would be the zero vector. So I'm glad you brought this up because this is the exact thing I'm trying to avoid. I only want to look at the vectors that are not zero, that when I multiply them by A minus lambda I get zero. The only way that happens is if this matrix does not have an inverse. So how can I tell when a matrix does not have an inverse? The determinant does equal zero. So here's how we're going to find the eigenvalues. I want to find the determinant of A minus lambda I, and I want to find exactly where it can't be inverted. So this thing right here is going to help us hunt for the eigenvalues. I'm going to make some alteration to my matrix A by subtracting lambda from basically a few of its entries along that major diagonal. And wherever the determinant goes to 0, that tells me that's where those eigenvalues are. Otherwise, I'm just looking for the 0 vector, and it's not a revelation to say if something multiplied by 0 is 0. I'm looking for the things that are not 0. I still multiply them together and I get 0. So that's the game. That's what eigenvalues really are. Can we go look for some? Okay. No. I can blame my problems on Hewlett-Packard today. Okay. So I want to find my eigenvalues here. So the way we're going to find those is through this. The determinant of A minus lambda I equals 0. So before we do that, we should build A minus lambda I. So I know what A looks like, 1, 2, 4, 3. What does lambda I look like? Lambda 0, 0 lambda. And if I put those together, I get 1 minus lambda, 2, 4, 3 minus lambda. So basically, the effect of subtracting lambda I is that it is going to happen along the diagonal from top left to bottom right. We're going to subtract lambda from each of those entries. Any questions about how we built this final matrix here? If we're good with that, how do we find the determinant?
Top left times the bottom right.
Okay, so 1 minus lambda times 3 minus lambda minus 4 times 2, and that equals 0. So let's do some distributing. 3 minus 3 lambda minus lambda, so minus 4 lambda plus lambda squared minus 8 equals 0. Lambda squared minus 4 lambda minus 5 equals 0. So what's lambda equal? Right, so this should factor into x plus 5, or sorry, x. Lambda plus 5, lambda minus 1 equals 0. Other way? Yes, okay. So lambda equals -1 and 5. Those are the eigenvalues. So let's be sure. Let's plug one of these in and make sure that that makes sense to us, because if it doesn't, then we don't really have eigenvalues. So let's start with lambda equals -1. Then that means that A minus lambda I becomes 2, 2, 4, 4. So if we did this right, then what should be true about the matrix 2, 2, 4, 4? The determinant better be 0, because that's the way that I manipulated this. Can you tell the determinant is 0? Even if you don't calculate it? Okay, so now here's what we're going to do. We found the eigenvalues tell us what values I can plug into this a minus lambda I to give us non-zero vectors that I can still multiply by a and still get 0. But now I got to find what those vectors are. So the way we do that is by finding a basis for the null space of the thing we just made. Can we do that? Can I find a basis for the null space of 2244? How do we do that? Yeah, let's reduce it. How can we reduce it? 1 from row 2? Yeah, let's do it twice. If we do that, then we get 2200. I think we can already be done. So now what's a good vector that can come out of that? Looks like 2x1 plus 2x2 equals 0. Or I could just divide everything by 2. x1 plus x2 equals 0. Or x1 equals negative 2x2. No, negative x2. So a few ways to kind of construct eigenvectors. But basically, here's what we know. Any vector where the first and second component are opposites is going to be fine, right? 1, negative 1 would do it. Negative 1, 1. 10, negative 10. As long as they're equal magnitude and opposite in sign, you're good. So what we've basically done is this. This should be true. 2, 2, 4, 4 times negative 1, negative 1 should be 0, right? And that's kind of like the last thing we can do to check that we did this correctly. I think this is true, right? We get 2 minus 2 and then 4 minus 4. So we found both eigenvalues and we found one of the eigenvector that goes with lambda equals negative 1. Any questions about how we did that? Right, so let's find the eigenvector that goes with lambda equals 5. So how do we go about doing that? Yep. Except now those values are going to change because I'm subtracting a different number. So minus 4, 2, 4, minus 2. I can tell that's linearly dependent, so we're good. So that's a good matrix. What should I do with it? Right. And this is something that if you do this right, this will always be possible. You should always be able to just eliminate at least one row. So in this case, if I add them together, which one do you want to keep? The one with the negative 4 or the one with the positive 4? Sounds good. 4, negative 2, 0, 0. So how does that help us get to a vector? Okay, so you basically divided the top row by 4? 1, negative 1/2?
Yeah.
0, 0. Okay, good. I agree. And then? So x1 minus a half x2 equals 0, or x1 equals a half of x2. And now you can pick any vector you want that fits that equation there. What was that?
2, 1.
I don't agree with 2, 1. 1, 2. This is one thing I will caution you about on eigenvectors, is that reversal is really common. So make sure that you actually have the ratio the way you want and not the opposite. But the way this is written, I need, since the half, I'm multiplying x2 by a half, so I need a double x2 to make that equation actually hold up. So we have lambda equals -1 corresponds to 1, -1, and then lambda equals 5 corresponds to 1, 2. So questions about how we got to the end of that? Okay. Let's go one more time. Let's just do one more by hand. Actually, do you know if your calculators will do eigenvalues? Is there like an EIG on there? Just MATLAB then? It's okay. It just robs you of the fun of finding them. All right. All right. Walk me through it. Or did you find it? No? Okay. All right. What should we do? Okay. So now let's build this related matrix. So -5 minus lambda 2, -7. 4 minus lambda. Right. So this is the thing we're going to be dealing with. What should you do with it next? Take a determinant. Okay. So the determinant of this will be -5 minus lambda, 4 minus lambda, plus 14 equals 0. So -20 plus lambda squared plus 14 equals 0. Did I give you something that factors nicely? I think so. All right, so I should have lambda equals -3 and 2, right? Is that color okay? I should have asked you a slide ago, but y'all see that? Okay. So now that I have my eigenvalues, what do I do with them?
You can put it in A5.
Yeah, so now that we have those lambdas, let's specify what the rest of our matrix looks like. So it should be -2, 2, -7, 7. All right, good. Does that matrix look okay? So what does it tell us about where to go next?
Yes, we can also. Should we also?
Yeah, I mean, we can. These are kind of parallel things. We can look at both at the same time. Plugging in the 2 gives us -7, 2, -7, 2. Make it really obvious that the rows are dependent on each other if they're the same. So it sounds like both of our eigenvalues are good. They give us these matrices that have linearly dependent rows. So I think we've confirmed both of our eigenvalues are correct. Now what should we do? Reduce, yeah, let's start with -3. How does it reduce? -1, 1, 0, 0. So essentially row 2 is 3.5 times row 1. Exactly, which means I can eliminate whichever row I care about and then scale the remaining one. So what does this tell us about a vector? X1 equals X2. And eigenvectors are never unique. You can define them in an infinite number of ways. It just has to fit whatever this parameterization says. So what would you like to call the eigenvector? 1, 1 is great. So lambda equals -3 corresponds to the eigenvector 1, 1. What's a good eigenvector to go with lambda equals 2? Or how did we get there? 1, -2/7, 0, 0. Cool, reduced. X1 equals 2/7 X2. And let's pick a vector that fits that. 1, 7/2. That's a good one. Probably not the one we were all thinking, but that doesn't matter. You have lots of choices there. Questions? All right. Let's go again. Let's at least start this one. I'm trying to remember why I didn't go straight to a larger one. All right, so let's see if we can finish this in 5 minutes. What do we do? Okay, so that makes this -8 minus lambda, 10, -5, 7 minus lambda. If I did take the determinant of that, I get Are these the same two eigenvalues that we just did, or is it opposite? Okay. I'm gonna go ahead and finish it because I think the eigenvectors are probably the part that is the most cryptic right now. So the eigenvalues that go with this are what? Okay. So let me get lambda equals -3, lambda equals 2. So for lambda equals 3, we get the matrix negative 5, 10, negative 5, 10. And for lambda equals 2, we get negative 10, 10, negative 5, 5. So from there, can we get eigenvectors for each one? How about for lambda equals negative 3? How can we handle that?
One, negative two, 0, 0.
1, negative 2, 0, 0. X1 equal to 2, x2. 1, 2. How are we doing? It would be. It's okay. I mean, it's a very, very common thing. So one thing I will encourage is that once you think you have your vector, plug those components back into here and make sure that they fit the way you want. Because that reversal is a pretty common thing. All right, how about the other one? 1, negative 1, 0, 0. Which says what? X1 is equal to x2. Or 1, 1 works. How we doing? Okay. Well, I got 2 minutes left. Let's go ahead and stop there. All right. Already told you about the test next Monday, right? Okay. So we got about 1.5 more sections to get through. Then we'll, if there's time left on Thursday, we'll review whatever you'd like.